Imagine 23 people in a room. If you gathered this crowd together and asked, what are the odds that any two of them share a birthday? What would you say? 5%? Maybe 10? The actual answer is over 50%. It sounds impossible. And if you have just 70 people, the probability jumps to 99.9%. This feels wrong because our brains are naturally self-centered. We look at a calendar and instinctively think about our specific birthday. When you enter a room, you are checking if anyone matches you. That probability is indeed very low, just 0.27% per person. Even with a few more people, if you only look at connections to yourself, the odds stay low. So we wrongly assume 23 people times a tiny percentage is still a small number. But that is the wrong math. The real question isn't about you. It's whether any two people match each other. With just two people, there is only one connection. But add a third person, and you don't just add one connection. You create a triangle, 3 pairs. With 23 people, we aren't making 23 comparisons. We are connecting everyone to everyone else. The web of connections grows explosively. In fact, 23 people create 253 potential pairs. That is 253 lottery tickets for a shared birthday. To calculate this easily, let's flip it. What is the probability that no one matches? The first person enters the room. They can have any birthday. 100% unique. The second person enters. To be unique, they must avoid that one day. They have a 364 out of 365 chance. We keep multiplying these fractions. 363 over 365. 362 over 365. As we multiply numbers less than 1, the total probability crashes. By the 23rd person, the chance that everyone is unique drops below 50%, which means the chance of a collision is over 50%. If we plot this for any number of people, we see the full picture. The probability doesn't grow in a straight line. It curves upward rapidly. Right here, at 23 people, we cross the threshold of more likely than not. So, why does our intuition fail us so badly here? It comes down to how we visualize connections. We tend to have an egocentric view. We place ourselves in the center. When we look around a room of 23 people, we subconsciously draw lines only from us to them. This creates just 22 connections. That feels manageable. And the probability of a match is tiny, about 6%. But reality doesn't revolve around you. In the birthday paradox, everyone is connected to everyone else. This creates a messy quadratic web of interactions. We aren't dealing with 22 lines. we are dealing with 253. That is where the probability hides. Our brains struggle to compare these two realities. We feel the 6%, but the math proves the 50%. This effect scales up incredibly fast. Let's look at the probability bar for larger groups. As we add just a few more people, the red bar shoots up. The number of possible pairs is exploding. By 41 people, we hit 90% certainty. At 57 people, 99%. And with just 70 people in a room, it is a 99.9% statistical certainty that two share a birthday. But when do we hit exactly 100%? That requires the pigeonhole principle. Imagine we have 366 boxes, one for every day of the year, including leap day. We can put one person in every single box. But as soon as the 367th person walks in, there are no empty boxes left. They must share a box with someone else. A collision is guaranteed. This math isn't just for parties. It is a critical concept in computer security, specifically regarding password collisions. Websites don't save your actual password. They run it through a hash function, a machine that turns text into a unique fingerprint. A collision happens when two different passwords produce the same fingerprint. This is a hacker's dream. This connects directly to our birthday problem. Instead of 23 people, we have digital fingerprints. The math is identical. Because of the birthday paradox, a hacker only needs to try the square root of the total possibilities to find a match. This makes attacks billions of times faster than brute force. Still skeptical? Let's leave the theory behind and run a Monte Carlo simulation. We will generate random rooms of 23 people and count the matches. After hundreds of trials, look at the match rate. It settles right around 50.7%. The math works. So what is the deeper lesson here? It's about the limitation of human thinking. We think linearly. 1, 2, 3. But in complex systems, interactions grow quadratically. When we graph people versus complexity, our intuition follows the blue line, but reality follows the red curve. It is in this massive gap between what we expect and what actually happens that paradoxes like this one exist. You will find this pattern everywhere, from social networks and genetics to traffic routing and digital cryptography. 23 people, 253 pairs. A coin flip's chance of a match. Mathematics reveals the hidden density beneath our linear intuition. Thanks for watching. If you enjoyed this visualization, hit subscribe for more animated math, and let me know in the comments which paradox should be visualized next.